Welcome to the second lecture of EE298, Generalized Principal Component Analysis. So today we are going to pick up what we have left last time, talking about principal component analysis. And we are going to study several extensions of PCA. So before we start, let's just go over what we have talked about last time. So last time we mentioned 4 challenges in modern data clustering problems. Can anybody still remember what are the 4 challenges? The first one. Yeah, curse of dimensionality, you know, the trend of dimensionality for multimedia, multimodal data will continue to grow. And the second challenge, somebody else? The chicken and egg dilemma, remember that picture? So you don't have the label, and then you also don't have the model parameters for the mixture model. So how can you do segmentation of unsupervised data? And what's the third one? Noise and outliers, right? So it will be much easier to ask you to segment data if your data in high dimension space is perfect. There's no noise, and then there's no corruption. But in real world, if you sample data from real systems, you're going to have a lot of noise and outliers in your data. And what's the last one? I assume everybody knows, but it's just, you know. The last one will be, you know, the ambiguity. You know, given a high dimensional data set, how are you going to make up your mind? You know, what's the classes of low dimensional model you are going to use? Are you going to use a very traditional Gaussian, or, you know, a little adventurous subspaces with some degeneracy in terms of the direction of the variation, or you want to use a more complex nonlinear model? Okay, so those are the 4 challenges. So you have to keep that in mind. And we also mentioned the goal of PCA is essentially to reduce the dimensionality of the data while trying to retain as much data variation as possible. Okay? And we also said that we can formulate the problem of PCA from 2 perspectives. And from the statistical view, we are saying the first leading principal components are given by the corresponding leading eigenvectors from the corresponding covariance matrix. Okay? And we also have a geometrical view. Essentially, PCA is trying to fit a small d-dimensional subspace model using a numerically efficient algorithm called a singular value decomposition. Okay? Those are some of the topics we have studied last time. So this time, we are going to pick up our discussion from last time. And we are going to first mention how to determine an optimal number for principal components to use. That is small d, right? From our observation, we only have capital D, right? We know the dimension of our ambient space. But what's the optimal number for the subspace, the dimension of the subspace we are going to use to fit the high dimensional data? And then we are going to talk about 2 extensions of PCA, namely Probabilistic PCA and the Kernel PCA. So if you read the textbook, we are going to have an extra section that talk about a very important problem called robust PCA, which is another extension of PCA, which deals with the problem of fitting low-dimensional subspaces while your data are corrupted, you know, and also may have missing coefficients. So this, in fact, is also the last one is a very important topic, and this problem shows up in many, many real-world applications. So we are going to, in fact, postpone our discussion to a later lecture to specifically discuss the robustness issue separate from the other problems. Okay? So let's start with the first problem we're going to talk about. That is, you know, after we have known how to at least solve PCA either from the statistical view or from the geometrical view, at the end, how to determine the optimal number of PCs we are going to use. So if you recall, so if I ask you to give me the optimal D-term approximation, you know, in terms of singular value decomposition of a matrix A, so what you are going to do is to look at the leading D singular values of the matrix, right? So in that case, it turns out that if your data is noise-free, then choosing the optimal number of PC is very easy. In this case, in this slide, I'm going to show you one example. Suppose in 5-dimensional space, I'm going to generate a 2-dimensional subspace. In this case, the 2-dimensional subspace will be spanned by 2 vectors, v1 and v2. Okay? So the first question is that do you have to worry about the linear dependency of v1 and v2? What's the probability that you generate V1 and V2 randomly based on Gaussian distribution. They are linear independent. The probability is very small, right? So in general, you don't have to worry about that, especially when the dimension of your data goes higher and higher. So then using these two vectors, I'm going to also randomly generate some coefficients. So I form a matrix, so which means the column vectors of this matrix is going to be a linear combination of V1 and V2, right? So that's my data matrix. I have 5 vectors in 5 columns. Then I'm going to call the command SVD in MATLAB. And the last line show you the singular values from the largest one to the smallest one. So if the data is perfect, noise-free, at least up to the machine precision, and you can see that only the leading 2 coefficients are non-zero, larger than 0. Okay, and then the smallest 3 coefficients are 0. You know, by just looking at the singular values, you can immediately make up your mind that for this database, for this type of data, I'm going to just use small d equals to 2, a 2-dimensional subspace, to approximate the distribution. Essentially, what you need to do is to recover the basis for the subspace, V1 and V2, or any arbitrary rotation of V1 and V2, such that the orientation of the subspace is still the same. So that actually goes back to the original PCA problem, once you have the D, right? But however, the picture is not that clear once you add noise in your data set. So in this case, I just copy the same A matrix from the previous slide, okay? And then I add some very small perturbation on the coefficients of the A matrix. That becomes a new matrix, AN, okay? Now I'm going to call the command SVD here. And you can see that although the leading 2 coefficients are still very close to the previous coefficients, singular values, right? But the last 3 coefficients become non-zero anymore. So which means you cannot use the simple rule of finding which coefficients, which singular values are non-zero, which singular values are 0, to make the determination that how large is your D is going to choose. So in this figure, I show you the semi-log plot of the values of singular value. So it turns out that in the noisy case, the decision to choose D becomes another problem of finding the knee point, the so-called knee point between the singular values, which means you compare the ratio and you find which coordinate will give you the largest ratio, the difference between adjacent singular values. Okay, so you can see actually another thing that you can imagine is that once you gradually increase the size of your noise, so the difference between this coefficient will become smaller and smaller, right? At the end, you are going to have a straight line in here, not as dramatic as this one. So at the end, the observation here is that with noise and outliers in the real-world data, so you normally should expect your data matrix to be full rank, which means there's no strictly 0 values in your singular values. Okay, so next we are going to say that, of course, with moderate Gaussian noise, if we do want to keep 100% fidelity of the data, we have no choice but use all the capital D dimensional original space to model the data, right? Because the matrix becomes non-singular, becomes full rank, which means if you do the singular value decomposition, as long as you drop any of the singular value, any of the components, right, you are going to miss some of the data, some of the accuracy. However, so in reality, if we can get away with keeping 100% of the fidelity, and we can still find trade-off between model complexity and the data fidelity. Okay, so how to do that? So first, we say that to model the data in fidelity, actually, that's fairly easy. So that's equal to, as we have seen last time, the sum of the squares of the error between my observation and my approximation xi. Okay, so that is equal to the Frobenius norm of the data matrix of the 2 data matrices x and x hat, right? Everybody agree? The Frobenius norm is just the sum of the squares of the entries of the matrix, and now, so if I'm going to choose small d to approximate my data capital X, you can see that this component will be the sum of the first D components in the singular value decomposition, right? So what's left is the rest of the component from D plus 1 to capital D, right? And last time we also said that the Frobenius norm of a matrix is equal to the sum of the squares of the singular values. In here, because by this subtraction, I have removed the first dominant small d number of singular values. So what's left will be from D plus 1 to capital D. And then the rest of that will be all 0. Okay? And what's the model complexity? A simple solution to tell you the model complexity will be simply choosing the subspace dimension D in here. Okay? Once we have these two guys, what we can do is try to minimize a objective function J1 that's equal to the summation of these two terms, both the data infidelity and the model complexity. Okay? Parameterized by a single coefficient gamma in here. So let me show you two extreme examples. For example, if I choose my model dimension small d equal to 0, so what does that mean? I choose subspace of dimension d equal to 0 to model my data, which means I treat everything, all the samples as an instance of the origin plus the error. So the difference between the sample itself, the absolute coordinate of the sample, and the origin is measured as the error. So in that case, d equal to 0, which means everything in the singular values is treated as the error. In that case also, but however, in that case, the model complexity becomes 0, which means the complexity is 0. It's as small as possible, right? So this term will dominate the objective function. Now, on the other hand, if I choose d equal to capital D, what will happen? If I choose small d equal to capital D, yeah, because I can just use the original canonical basis of my ambient space for as the basis of my subspace, then I don't lose any information. On the other hand, so the small d becomes capital D. So this term becomes extremely small, actually goes to 0. And then this term becomes capital D. So this term dominates the objective function. So you can see by choosing a proper gamma and minimizing this objective function is trying to find a balance and to simultaneously minimizing this term and this term, right? You find a local, try to find a local minimum that minimizes this objective function, okay? Such that you can achieve a balance between this term and this term.
Was there some justification for just a linear, like just a constant gamma of d, or is that just one possible?
It's just a simplification. Yeah. So yes, a very good question. The question is why we choose a summation in here and then parameterized by a single gamma. So actually, in the next slide, you're going to see that there are more precise models for you to use. So they are more complicated than this form. So this is just a very raw definition of the so-called model selection problem to choose a low-dimensional subspace. So to answer your question, in this slide, if you look at the appendix of the book, you are going to find several more principal conditions to help you to optimize the dimension of the subspace. So in the textbook, we have seen 3 conditions. The first one is called Bayesian information criterion. And the second one is Akaike information criterion. And the third one is extension of the AIC called the geometric AIC, which was proposed around 2000 and 2003. So in fact, if you want to derive these 2 conditions, the derivation will be much more involved. So in this course, we are not going to mention the derivation of this condition. But the application of these conditions are very straightforward. And they are very convenient to use. So you have your data, and you can try to optimize any of these coefficients, any of this condition, to try to help you to find the optimal D for the dimension of this subspace. So in practice, we have observed that using this geometric AIC to fit low-dimensional subspace model to help you to choose the dimension for subspaces tend to slightly perform better than the first 1 and 2. So if you're really interested in the derivation of the geometric AIC in particular, so certainly you should look into the Kanatani's paper in 2003. It's a conference paper. And there's one more fun fact, that is that if you observe the 3 equations, in addition to the first term, it's nothing but the data infidelity, right? So we have explained. So you are going to see a constant that appears in all the equations. That is capital DV minus D squared. So how does this constant come from? So this is, in fact, is known as the number, the dimension of the Grassmann coordinates to specify a small d dimensional subspace in capital D dimensional space. Can anybody understand why this is true? Suppose I ask you to specify a subspace, small d dimensional subspace. What you can do is to give me small d number of vectors, and they are linearly independent, right? So they form a capital D times small d dimensional matrix, right? Of course, if you want to directly record, you want to directly save the describe the orientation of the subspace, you have to save all the coefficients in this matrix, right? But remember, if you do any scaling and linear combination between the row vectors of this matrix, you are not going to change the orientation, right? Because they are linearly independent. Therefore, any linear combination by multiplied by a scale or a linear combination of the rows will not change the orientation of the subspace. So what you can do is to use, so let me write in here. So suppose you have an A matrix in here. So this is, let's say, small d times capital D. So they're row vectors. So what you can do, remember, is to look at the first d times d dimensional submatrix. So what you can do is to use Gauss elimination. Apply any linear scaling and the linear combination between the rows, and then you can try to diagonalize the submatrix in here, right? So now you have another matrix becomes I and something in here, right? And after the Gauss elimination, you can see that this one is fixed. So in order to describe the coefficient of that describe the subspace, you only need to save the coefficients in the second submatrix. So the number of coefficients in this matrix will be capital D minus D squared, right? Is that clear? It's due to the fact that you try to do any linear combination between the basis vectors, although they change the value of the basis vector, but after the operation, the vectors remain linearly independent. So that's the basis for Gauss elimination. Okay. So the second topic we're going to talk about is try to extend the formulation of PCA from a generative approach called the probabilistic PCA. In this case, let's suppose all the observations x are generated by this equation, x equal to x0, which is the mean, and then plus ud is the basis for the subspace, small d dimensional subspace, times the coefficient y plus epsilon, which is the noise. And we are going to further assume the random variables, and then they are random variables. And we're going to assume that the y and the epsilon are independent. Okay? So next, we are going to assign some the probability distribution to these coefficients. Let's assume y is the normal distribution. with mu y and sigma y. And then epsilon is a noise term, of course. Naturally, you are going to assume the mean is going to be 0. And then it has its own covariance matrix, sigma epsilon. Okay? And then the parameters for the observation can be solved by the following equations. Okay? Is this clear? For example, mu of x is equal to the expectation of x. So you plug that in, you immediately get that equation, right? So x0 is constant, so nothing you need to compute. And this is a linear operation, so you can bring the expectation to the second term. So it's the expectation of y is nothing but the mean of y. And the mean of epsilon is 0 plus 0. So that's the first term. Okay? And do we have to explain the second term? Okay. So the covariance matrix of x is equal to the expectation of x minus mu x, x minus mu x transpose, right? So it's equal to expectation of no, it's actually say
y minus mu y.
Yeah, it's equal to u dy plus epsilon, u dy plus epsilon transpose, right? So it's equal to, so we have 4 terms. So if you carry out the computation, right? But
there's got to be a mu y in there as well. So I think it's ud times
mu y.
y minus mu y.
So let's see. So it's equal to E of, so you plug this one in. It's equal to x0 will cancel each other out. Will be u dy plus mu minus u d mu y. And u dy, thank you, minus u d mu y transpose. Okay? So this is constant, right? And this is constant. And you also further realize that because we assume that the random variables, they are independent, so the product of these 2 terms, so is equal to the expectation of the individual terms, right? But however, the expectation of the epsilon is equal to 0. So that 2 terms also disappear. At the end, you only have 2 terms left. That is the expectation of, that's actually what I just wrote, equal to, you can further bring this ud out, ud y transpose ud. Oh, actually, you have to move that in here. So it's mu y, I guess, transpose. So that gives you this term. And then the last term will be this 2. So it will be the expectation of epsilon transpose that will give you the covariance matrix of the air term. Okay? But however, if we look at this equation, suppose we can compute from my samples the mean and the covariance, but there are still ambiguities how to assign those values to these 4 terms, right? So the solution is not unique, right? So from the sample mean and sample covariance, you will not be able to uniquely determine the coefficient you want to solve. So which tells us that we need to further simplify our model. So in this case, if we assume that y is standard normal and then epsilon is isotropic, then we can further eliminate the terms in here. So if we go back, if we assume that y is standard normal, so the mean of y is equal to 0, right? So we eliminate this term. And second, we assume that the noise is isotropic, which means this one becomes a diagonal matrix, like the following. Okay? And then also this one becomes identity matrix. So then each observation is also a Gaussian distribution that can be written down like the following. Right? Agree? So next we are going to compute the log likelihood. So the definition of log likelihood given n samples is just the log of the product of the probability of xi. And because you can bring this one in, and then you can write it as L equal to log of the product of I equal to 1 to n P of xi. So it's equal to the summation I equal to 1 of n of log P of xi, right? And you bring the probability of Pxi like the following into that equation. You will end up with 3 terms, right? The first term will be this term. The second term will be this term. And then the last term will be this term. Okay? So if you remember this equation, is this clear? This one is easy to understand, right? And this one is also easy to understand, okay? Because the minus is over here. So it's 1 over 2 pi. So this is the power to the power of n divided by 2. So this is the determining of the covariance matrix. What is this guy? So remember, last time we have this property that x transpose AX is equal to the trace of AX transpose, right? And then you apply that to n samples. That's what you have. Right? So you apply that to this equation. This is equal to the trace of this term times this term times x minus mu of x transpose. And then you have n terms. Okay. Now, as we said last time, that if I take the gradient of take the partial derivative of L with respect to my coefficient ud, we are going to find the stationary points. So I'm going to take the partial derivative of L with respect to ud and then set it equal to 0. And let's see. So the first term has nothing to do with UD, will go away, right? And what happened to the second term? So let's do a small exercise here. Log of determinant of the covariance matrix of X partial UD equal to one of, so just do it by the chain rule. Right? So it's equal to. So by the way, what's the derivative of the determinant of a matrix? It's equal to the. If you check your mathematical manual, to determine of the matrix times the trace of, let me see if I remember that correctly. Nope, there has to be a sigma inverse here. So that actually is the chain rule. So these two cancel out. And what is this? Because we know that the covariance of X is equal to this equation. So this inside gives you 2 times UD, right? So that's it. And then 2 cancel out outside. So that is this term. Okay? Is this clear? Unfortunately, no. So that's why I wrote this down for you, although not very pretty. So how to derive the second term? So remember, we already have a tracing here, so we can later on combine with the second one. So the trace, partial derivative of a trace of X hat. What do I compute? I compute this guy. Okay. So what I can do is that I bring the derivative inside the trace. Partial X minus 1 inverse. Okay. So this term has nothing to do with UD, right? This one is a constant matrix. So I can bring this out. And now you also need to go back to your math dictionary to find out what's the rule to take derivative of the inverse of a matrix. It turns out that it's equal to minus the inverse of sigma x times the derivative, the partial derivative of sigma x without minus partial UD, and then you have the second copy. That's very similar to the one-dimensional, the functional derivative, and then we have the rest. Sorry, I'm writing into the projector. The screen is equal to this, right? And we also know that. So let me write it in here. So equal to the trace of. So we already know what's this one, right? So we get 2 copy. We get a 2 UD, and 2 will cancel out. So equal to 2 of UD of x is equal to this equation, right? And next, we know that you can arbitrarily change the order of the matrix inside the trace. That gives you this one, right? So you move these two terms to the right-hand side, and then you get that equation. So at the end, from taking the partial derivative of L with respect to UD, you get this equation. Okay? And then you can also eliminate the inverse of sigma x, and then you get this constraint. Is this clear? Okay, so now, so we need to find how to solve UD using this constraint. So there are, in the textbook, you are going to find that it says there are 3 possible solutions. The first solution that satisfies this equation, remember we are trying to find UD, okay? So the first equation is for UD equal to 0, right? That satisfies this equation. However, that violates the assumption that we are trying to find linearly independent vectors that span a d-dimensional subspace, okay? So that is out of the question. So that leaves us to the rest two possible solutions. The first possible solution is for the matrix in front of UD equal to identity, right? So that identity times UD equal to UD. So in that case, which means the sigma hat of x is equal to sigma x. And then we know that this is the definition for sigma x, right? That's the second equation here. So now we move. So if we move the second term to the left-hand side, we get the third equation, right? You have to follow me. And next, I'm going to multiply both sides by UD. And because I assume that the UDs are linearly independent, so that gives me a diagonal matrix, capital lambda. So I multiply both sides by UD, and I get this equation. So as I mentioned last time, if you see this type of equation, a matrix times UD equal to UD times a diagonal matrix, it means UD is the eigenvector of this matrix. Because each column vector of UD times this vector is equal to the corresponding, the same column vector of UD times the scalar E in capital lambda. Okay? So next, you remember that this sigma corresponds to the noise. So we want the noise to be as small as possible. Okay? So if this is something we can compute, it's fixed, and then we don't know this one, but I want to minimize this one, what I can do is to maximize the singular value, the eigenvalues of this side. Yes?
Back up one step. So the UD are the eigenvectors of sigma hat x. So what happened to the other term inside the brackets?
Oh, because this, yes, good question. So the other term, there's a second term in the bracket, because this is also a diagonal matrix. So it doesn't affect the fact that it is still a single vector. Right? So that's a good question. So if you don't believe that, you can just write down, you can just write an example and then convince yourself. Okay? Now, as I said, UD is an eigenvector of sigma hat, and necessarily is an eigenvector of sigma hat minus sigma squared times ID, right? But this is a diagonal matrix. So now remember, I want to minimize the noise, the variance of the noise. So what I can do, because this term is fixed, so I can choose a very large number in this side, such that in order to achieve equality, this one necessarily will be small. Agree? So what I can do is to choose UI, U1 corresponds to the largest eigenvalue of this guy. Okay? And then what is this? This is another matrix that to make sure that UD transpose UD equal to capital lambda. Okay? So this one will just make sure that this is true. So we bring this one, we bring the equation into this condition. So we have this equation transpose U1 equal to lambda, right? And these two cancel out because they're eigenvectors. They are orthogonal to each other. So that gives me, that gives me this equation. Okay? So that tells me these two, then this equation equal to so equal to this guy, and this guy is equal to this guy is equal to UD transpose UD. So you plot this one in, and then you get this equation. Okay? Is this clear? Let's see. So we know that the sigma hat x minus equal to what? This guy equal to UD transpose, right? So it's equal to U1 this guy transpose U1, right? And then you move this two term to the left hand side. That's this equation. Is that clear? Any questions? And because this matrix corresponds to the eigenvectors of sigma hat of x, so that becomes sigma 1, which is a diagonal matrix that corresponds to the eigenvalues corresponding to U1. And then the second term, these two will cancel out, and then that gives you the second term. Okay? And with that, it tells you that because this is diagonal matrix, so you can take, so this makes sense. You can take the square root, right? Which means you just take the square root of the diagonal coefficient. So which means this guy is a diagonal matrix, as we have already known, and is equal to the square root of this equation, of this matrix. And then because UD equal to U1 times this guy, so it's equal to U1 times the rest of the equation. Okay? And how to get to the last one? Are there any questions regarding any of these steps? So if you look at the textbook, it will be more concise than this one. So it's better we understand everything, in the class, rather than leave it. No questions? Okay. So how to get the last one? In order to see how you can get the last one, you only need to observe that because UD is equal to UI times sigma 1 is a diagonal matrix that collects the first D largest eigenvalues of sigma hat x, right? So what's left is the rest of the eigenvalues, because this is only a scalar. So which tells you that in this computation, the rest of the eigenvalues of sigma hat should be equal to each other, under the assumption that the noise is the isotropic Gaussian distribution. Okay? So this is the second solution, possible solution. So there's a third possible solution if sigma x is not equal to sigma hat of x, but we can still have this constraint, right? That is our assumption, based on the simplified assumption about the distribution for y is a standard normal, and then the distribution for the noise epsilon is isotropic. So that gives us this equation, right? And then you multiply this equation from the right by UD, and then you get this equation. It's equal to UD transpose times UD plus sigma times UD, right? Because previously we know that UD transpose times UD is equal to capital lambda, so that's capital lambda. Okay. Now I move this, and then next I'm going to move this equation to the right-hand side. I get this equation, right? And after that, I multiply both sides by sigma hat. I get the next equation. We are here, okay? Now we use the constraint. Now we use the constraint regardless if this is identity or not. And then, of course, UD is not going to be 0. So if that's true, this equation, this portion of the equation is equal to UD, nothing but UD. Okay? And I move this term to the left-hand side, I get this equation. You can see that if even I don't assume that sigma hat x times the sigma hat inverse is equal to identity, I still get back to this constraint. So where's this constraint? This constraint is used right here. This constraint is used right here. Where is it? right here. So we go back to the solution here. So you can see at the end, these are our solutions for UD, which is the basis vectors for the subspace, d-dimensional subspace, and this is the solution for sigma, for the noise. Okay? So that's it. Whew, a long derivation. Are there any questions before we move on? So as I said, the textbook will be more concise than this one. So
is it possible to maybe to see some structure in that sort of just makes sense? Hopefully this should like make some sense. This result is like based on based on maybe a simplified example.
unfortunately, it has to be written like this way. So it's not as clean as geometric in the previous in the first lecture, because the formulation for the first lecture are straightforward and easy to understand, but this is not. So the benefit of that later, if we have time to discuss, is that if you can formulate PCA based on a probabilistic framework, then if you have a mixture of Gaussians, mixture of subspaces, then you can assign probability for the membership of a sample to be, for example, a half of this Gaussian, a half of that Gaussian. Then you can also fit that mixture of Gaussian problem using that. So if you do that by solving a mixture of Gaussian model, so using this formulation, I think that you will have a more principal solution than the other methods. Okay. Are there any questions? Okay, should we move forward? So the next extension we're going to talk about today is Kernel PCA. In this case, if the underlying distribution of the data becomes nonlinear, of course, it doesn't make sense to directly apply PCA to find a low-dimensional subspace. Of course, in any case, you can still do that, but the dimension you have to use for fitting a subspace on a nonlinear distribution, the dimension of the subspace you are going to find in order to achieve a good data fidelity will be necessarily much higher than the intrinsic dimension of the nonlinear data, right? So what we hope for in this case, in this extension, is to find a nonlinear map, phi in here, such that I'm going to map the data from capital D dimensional space to a capital M dimensional space. And our hope is that after the mapping, the structure of the embedded space becomes linear. I'm going to give you an example in the next slide. Okay. So in the embedded space, because the distribution becomes linear, then we can apply PCA to the embedded space, and then we can extract some more meaningful linear structure in the embedded space. So in that case, what do I mean by that is I'm going to apply PCA on this matrix. So the column vector of this A matrix becomes the projected vectors phi of x1, phi to x2, all the way to phi of xn. Okay? So let me give you an example. So suppose in a two-dimensional space, all the samples satisfy a second-order conic constraint. That is this equation, c1x1 squared plus c2x1x2 plus c3x2 squared plus c4 equal to 0. So this, of course, doesn't define a linear subspace, right? So in R2 space, a linear subspace can be either the origin or a line or the total space. But this equation doesn't give you any of the linear structures. So what we can do is to define an embedding function phi, such that I'm going to map x1, x2 to z1, z2, z3, So what are those points? Those points are, the coordinates are x1 squared, x1, x2, and x2 squared. Okay? That's easy enough. So this is a complete list of the so-called ordered monomials of second degree in R2. Okay? So after that, you can see that the constraint becomes C1, Z1 plus C2, Z2 plus C3, Z3 plus C4 equal to 0. Okay? So that gives you a affine subspace in three-dimensional space. It is affine because there's a constant term in here, right? And how can you recover a linear subspace? If I said that this condition also defines a linear subspace, where is this linear subspace? In four-dimensional space, right? So if you add Z4 in here, equal to 0, that makes it a linear subspace. Okay? So in geometry, it means that you are going to add a homogeneous coordinate in here, that you can move a affine subspace to become a linear subspace. Now the next question, next quiz, is how to recover the coefficients. Suppose I give you a lot of those points, sample points. x1, x2 equal to x11, x12, x21, x22, and give you a lot of those examples. How can you tell me the coefficients for C1, C2, C3, and C4? Of course, singular value decomposition will going to help you. Yeah, PCA, but it's going to find the basis for the subspace. But these coefficients are not the basis. So what are those coefficients? Those coefficients tell you a basis that's perpendicular to the subspace. Equal to 0, which means if you treat Z1, Z2, Z3, and if you treat C1, C2, C3, and C4 as another vector, it means the dot product between the points, the sample points on the subspace, and the vectors C1, C2, C3, and C4 equal to 0, which means this vector is perpendicular to that. So what you're looking for, of course, you can apply singular value decomposition, but you're not looking for the first. You're not going to look at the first several column vectors. You're going to look at the last one that tell you the null space, right? So in fact, what you're going to do is exactly the following. So you're going to do the projection, and of course, as I said, you need to add a homogeneous coordinate 1 in here. So this is going to be the last coefficient because it's always going to be 1, right? Because you know that the last term is C4, right? So you're going to compute the null space of this matrix. That give you the coefficients C1, C2, C3, C4. Is that clear? So in fact, this embedding function is very special. So it's known as the Veronese embedding. Okay. So given x, so the nth degree Veronese embedding is defined as the list of all the nth degree monomials in capital D dimensional space. One example we have just seen is just this guy. This is the second order Veronese embedding in the R2, in R2 space. Okay? So next, so as I said that using embedding, because we may often assume that the original dimension of the ambient space, capital D, is already very large. If I'm going to use a map to embed the samples into a higher dimensional space, the dimension of the embedded space will be even higher, right? So that's the problem, the dimensionality problem. So the nonlinear embedding doesn't actually help you to reduce dimensionality. It actually give you a higher dimensional space for you to operate. So the next question I want everybody to think about is, what's the dimension for the Verneza map? So this is the basic rule. So if I tell you capital D, I tell you small n, how many terms we're going to have after the Verneza map? So this problem boils down to, so if you this is much better. So in capital D dimensional space, okay, so you have x1, x2, 2xd, okay? So in order to figure out how many terms you have after a n degree Verneza embedding, is to figure out what is d1, d2, and dn, such that di has to be all larger and equal to 0. And the summation of di is equal to n. How many such terms satisfy this constraint? There's a very similar problem in the probability that you can directly apply that can give you a direct answer to that. Can anybody recall any of the classic solutions you learned from the course of probability that you can directly apply to this problem? Okay, let me give you another hint. Suppose you treat those guys as cells, and you treat those the orders, the degrees of the coefficients as balls. So this problem becomes, you have capital D cells. You want to fit in n balls. So this is the so-called D cell n ball problem in probability, right? So which means, right here. So that's the solution. So if you know that you are solving an n-ball D cell problem, how do you get to this equation? Exactly.
Like balls are one object and the partitions are another object.
Exactly.
And, yeah, it's like representation.
So if you forget, the standard solution is to treat cells, the divider of the cells and the balls equally. Okay. So you're going to have. So if you have D cells, you're going to have D plus 1 dividers, and then you're going to have n balls. And any arbitrary order of balls and the dividers are going to give you a valid solution and a unique solution without distinguish the different balls and the different dividers. Okay. On top of that, you know that the first divider is always fixed. You cannot have this. You cannot have balls outside the first divider, and you also cannot have the balls after the last divider. So these are fixed. So you only have D minus 1 possible way of arranging dividers. So that gives you the total number of objects you can arrange to be n plus D minus 1. Okay? Out of that, you choose either n or D minus 1. So that's the solution. Okay? So as you can see, so this n choose m, this number will easily blow up when you have large capital D or large n, right? So now the question is, can we find the high order nonlinear structure without explicitly calling the embedding function? Which means, can we apply PCA on some structure of the data without specifically construct the high dimensional data, without spending resources to store and call the embedding function. Okay. So that actually is the topic for the next algorithm called nonlinear PCA. And I think that we can probably stop here today. Okay. Thank you very much.